Welcome back to the deep dive. We are returning to the Alita architecture today. And, well, based on the V2 documentation we're looking at, the engineering team has hit a fascinating, incredibly difficult wall.
They absolutely have. And for those of you who've been asking for an update on Alita, this is exactly what you've been waiting for.
Right. The source material we have on the desk today is titled Podcast Update V2 Metrics Reset plus Contract Hardening.
Uh,
And it details the transition from Alita as a concept, to Alita as a hardened autonomous AI agent. And I want to be really clear here before we dive into the technical specifics. I need to establish some firm ground rules for this session.
oh, definitely. We have to set the boundaries today.
Yeah, because we are strictly dealing with an update to the previous document, which was Alita, the unfinished intelligence. And because this is an advanced session, we are absolutely not going to rehash the basics.
No, we really don't have the time to go backward today.
Exactly. So we're not doing a reintroduction of the 5-year-old child cognitive model. We are not reviewing the ghost architecture, and we're definitely not spending 20 minutes explaining the foundational philosophy of hallucinated competence again.
Right. The VDM D22D2 text is our sole focus today.
Exactly. So look, if you want to know about the 5-year-old model and how her core philosophy started, you need to hit pause right now, go back and check out our previous deep dive on Alita. Today is exclusively about what happened next.
I think that's the right approach.
Yeah.
Because the jump in complexity from that first document to this V2 update is it's substantial.
It is massive.
It really is. We are moving from theory into the actual and glamorous trenches of software engineering. The core theme of this update is it's a massive structural evolution.
Yeah.
The engineers are attempting to take a collection of very impressive but ultimately isolated prototype experiments and, force them into a completely closed feedback loop.
Which brings up a massive reality check that the document actually hits you with almost immediately. I mean, building an AI that actually knows what it doesn't know sounds incredible in a white paper.
Well, it's the holy grail of artificial general intelligence.
Right. But in practice, it is so impossibly messy that the engineering team literally had to wipe her memory to move forward. They executed a hard reset on her metrics just to stop her from learning the wrong lessons. So I guess the first question is, why was the before picture so problematic that it required a total memory wipe?
Well, to understand the necessity of the wipe,
Mm-hmm.
you really have to look at the architectural shift they're trying to pull off here. In the early phases, the iterations we discussed previously, Alita was highly capable, but she was fragmented.
Okay, fragmented how?
Think of it as an AI with individual siloed skills. You had a standalone optical character recognition system, or OCR.
Right, and OCR is essentially forcing the AI to look at the screen, pixel by pixel, to read text or identify UI elements, right?
Exactly. So that OCR system was interacting with a 3D program like Blender, but then completely separate from that, you had isolated voice commands. And in another corner, you had separate Python scripts for execution and entirely different scripts for logging what happened.
So it proved that she had the capability to do these things, but it wasn't a cohesive entity. It sounds a bit like having a team of brilliant freelancers who all work for the same company but refuse to use the same Slack channel or share their project files.
That is an incredibly accurate way to frame it. I mean, having a bot that can read a Blender menu or execute a Python script is functionally useless for true autonomy if those actions aren't feeding back into a centralized, measurable nervous system.
Right, a standalone skill is just a party trick at that point.
Precisely. A
Yeah.
party trick. The massive architectural pivot detailed in this V2 document is the move from those isolated skills to a closed feedback architecture. The entire system is now governed by a very strict, unforgiving structural cycle.
And the document outlines this new mantra of autonomy as a 6-step loop. It goes: observe, execute, measure, analyze, learn, retry. Every single subsystem has to pass through that exact pipeline.
Without exception.
But what does that actually change fundamentally? Because legacy models observe and execute all the time. I can give a standard large language model a prompt, it observes the prompt, and it executes a response. How is this 6-step loop any different from what is already on the market?
The critical difference lies in the mandate of responsibility, specifically in the measure, analyze, learn portion of that loop.
Okay, explain that.
A standard LLM is essentially a stateless text predictor. You press a button, it generates the most statistically probable text based on its training data, and then it stops.
It just washes its hands of the whole thing.
Exactly.
Yeah.
It has no intrinsic mechanism to measure if the code it just gave you actually compiled successfully on your machine. It doesn't analyze the stack trace of its own failure unless you, the human, manually copy and paste the error back into the chat window.
Right, you are the one closing the loop for it.
You are. By forcing every single action through the observe, execute, measure, analyze, learn, retry cycle, the V2 architecture is mandating that Alita takes computational responsibility for the outcome of her own actions in real time.
Give me a tangible example of how that changes her behavior. Like, how does this look in practice compared to the old, siloed version?
Look at how voice commands are handled now versus then. In the old setup, voice commands were just a trigger. You would speak a command, the system would attempt to execute it, and it would drop a simple line in a text log saying the command was heard.
So it's open loop.
Completely open loop.
Yeah.
In V2, voice commands are fully integrated into the main execution pipeline. When a command is received, it doesn't just log it. It generates standardized telemetry, it predicts an expected outcome, executes, and then measures the actual outcome against its own prediction.
What about error handling? Because I imagine forcing an AI to analyze its own errors without human intervention requires just a massive amount of overhead.
It does, and that is where the new decision engine comes into play. Previously, if Alita threw an error during a complex task, the script would halt. A human engineer would have to open the console, read the raw logs, figure out what went wrong, and then manually adjust her parameters or rewrite her scripts.
The human is the troubleshooter.
Yes. Yeah. Now, errors are intercepted automatically. They are assigned specific reason codes, which we will get into deeply, and they're classified by the decision engine. The system categorizes the failure autonomously so it can decide what to do next without a human typing in a new prompt.
I want to push back on one of the examples in the text here, which is the automated tutorials. The document claims that previously, a human had to tell her to enter a course mode to learn a new concept. Now it says the system automatically suggests tutorials when it detects a knowledge gap.
Yes.
Are we talking about the AI literally deciding to go to school because it realized it failed a task? How does a machine even conceptualize a knowledge gap?
Well, it doesn't conceptualize it the way a human does. It quantifies it.
Quantifies it how?
Let's say Alita attempts to execute a task, applying a specific subsurface scattering texture in Blender, for instance, and she receives a sequence of validation failures. The loop immediately triggers the analyze phase.
Okay.
The decision engine looks at the telemetry, sees that the tools are functioning, the API is responding, but the specific execution sequence is repeatedly failing. The system concludes mathematically that the failure is not a hardware issue or a syntax error, but a lack of operational knowledge.
It rules out the plumbing to realize the operator is the problem.
Exactly. At that point, the loop moves to the learn phase, where she actively proposes querying external documentation or entering course mode to acquire the missing procedural steps.
Which means she has to know unequivocally that she failed. And that brings us to the most dense and arguably the most important section of this entire update, the telemetry revolution and the RN lifecycle. Because if an AI cannot measure its own success objectively, it simply cannot become autonomous.
That is the absolute bedrock of the V2 update. You cannot build a self-improving system if the system relies on subjective human feedback to know if a code change made things better or worse. The developers had to introduce an entirely new core layer beneath everything else, the telemetry infrastructure.
The document breaks down the anatomy of what they call a run-N, and we need to spend some serious time unpacking this because this is where the engineering gets incredibly rigorous. Whenever Alita does anything now, it is encapsulated in a strict life cycle.
Yes, a very rigid sequence.
It starts with a run-start event, then the actual action takes place, then there is a result, and finally a run-end event.
On the surface, that just sounds like standard software logging. What makes this a revolution for an AI agent?
It's revolutionary because of the required data payload inside that run-end event. In standard software development, logs are often unstructured text. A developer writes console.log task complete or print error 404.
Right, it's designed for a human to read later over a cup of coffee. Precisely. But human-readable text logs are terrible for machine learning. You cannot easily train an AI on millions of lines of unstructured, inconsistently formatted text.
So what does Alita's payload look like? If she's not just dropping a text string into a log file, what exactly is she reporting back to the system?
When a run-end event is triggered, it must capture a highly specific, rigidly formatted JSON payload.
JSON being JavaScript object notation, just for anyone not familiar, it's a way of storing data in strict key value pairs.
Right, it's structured data, and our payload requires fields like outcome status, reason code, error type, reason subtype, evidence flags, and retry indicators.
Let's drill down into that because I want to understand the computational weight of this. Take outcome status. In a normal script, something either works or it doesn't. True or false. Pass or fail. Why does she need a complex multi-state outcome status?
Because autonomy requires nuance. A binary pass-fail doesn't tell a self-correcting system what to do next.
Okay, give me an example.
Imagine she is trying to download a file. If it fails, a binary system just says false. But a multi-state outcome status combined with a reason code provides actionable intelligence. Did it fail because the server timed out? Did it fail because her local drive is full? Did it fail because the URL was malformed?
Ah, I see. Each of those requires a completely different autonomous response. If the drive is full, she needs to delete files. If the URL is bad, she needs to search for a new link.
Exactly. And the document lists some of these new granular reason codes. Things like action not found, unknown, task terminal guard, or validation failure.
This fundamentally changes her behavioral history, doesn't it? It turns every mouse click, every API call into a fully auditable, structured data point. It's less like a text log and more like a black box flight recorder.
A flight recorder is the perfect analogy. And the reason they had to go to this extreme level of detail is because of a concept called contract-based execution. This is where the V2 architecture dramatically diverges from standard large language models.
Explain the execution contract. Because my understanding of an LLM is that it's inherently probabilistic. It guesses the next token. How do you force a probabilistic engine to sign a rigid data contract?
It is incredibly difficult, and it creates a massive amount of computational friction. The new architecture dictates that Alita can no longer just perform an action, output a block of text, and wait for the next prompt. Every single action she takes must return that minimum set of telemetry fields we just discussed.
So it's not a suggestion, it's a binding engineering contract.
It is absolute. If she performs the task, she owes the decision engine a perfectly formatted JSON receipt, detailing exactly how it went.
Okay, but what happens if she fails to generate the receipt? What if the LLM hallucinates and outputs a beautifully written paragraph about how successful she was, but fails to format it as a JSON payload with the correct reason code?
Then the action is classified into that task terminal guard state you mentioned earlier.
Yeah.
The system essentially rejects the entire run. It doesn't matter if she actually achieved the goal in the 3D software. If she cannot report the telemetry in the exact contracted format, the system treats it as a critical failure.
That seems incredibly punishing. You are telling me that the system will throw out a successful piece of work just because the paperwork wasn't filed correctly.
Yes, because in an autonomous, closed-loop system, an undocumented success is just as dangerous as a failure.
Really? How so?
If she randomly succeeds at a complex task, but the system has no structured telemetry explaining how or why she succeeded, she cannot learn from it. It becomes impossible to replicate the success reliably. The contract ensures that the state, the reason, and the context are intrinsically and mathematically tied to the action itself.
Okay, so she's building this massive, rigorous, empirical database of her own competence. She has flight recorders on every subsystem. But this extreme level of data hygiene led directly to the most dramatic event in this update, the hard reset.
Yes, the metrics reset.
We really need to talk about the necessity of wiping her historical metrics. If data is the lifeblood of an AI, why on earth did the developers intentionally throw away all of her past learning? It seems counterintuitive.
It does seem drastic, but it comes down to what the engineering team identified as the pollution problem. It's the reality of iterative development. When you build an AI over months or years, the early versions generate a lot of data.
Right.
Those loosely connected prototypes we talked about, the early OCR tests, the isolated Python scripts, they were generating logs. But those logs, which the document refers to as legacy runs, did not adhere to the new execution contract.
Because the contract didn't exist yet. They were just unstructured text files or basic Boolean pass-fail logs.
Exactly. The legacy data had incomplete contract fields. It utilized old, deprecated error structures. Even worse, it was a messy, untagged mix of experimental test runs, developer interventions, and genuine autonomous successes.
But couldn't they just write a script to parse the old data and map it to the new format? I mean, why take the nuclear option of a memory wipe?
Because you cannot reliably backfill intention. If you have an old log that says a script failed, but it doesn't have the granular reason code or the evidence flags, A parsing script has to guess why it failed.
And if you guess wrong,
If you feed guessed data into a highly sensitive decision engine, you poison the well.
poison data in reinforcement learning, that's catastrophic.
Precisely. Imagine the new decision engine trying to build a statistical model of her reliability. It looks at her history to figure out what she's good at and what tutorials she needs. But the database is filled with half-written receipts, corrupted files, and false negatives from early prototype testing.
So she's basically reading a textbook full of typos.
Yes. If she analyzes a past failure, but the reason code is missing because it was an early run, she might draw the completely wrong causal conclusion. She might think she's terrible at Python when in reality, the early Python tests failed because the developer server was offline.
That makes total sense. Bad data actively trains the AI to make bad decisions. So the developers executed the clean learning window.
It was a dramatic but architecturally necessary solution. They took all the historic legacy data and completely severed it from our active decision engine. They archived it, locking it away strictly for offline human research.
A clean break.
Exactly. From the moment the hard reset was initiated, only runs that strictly obey the rigorous V2 execution contract are allowed to register in her memory.
But wiping the slate clean introduces another layer of complexity. The document details the challenge of cohort separation, because when an engineering team is testing a newly wiped AI, they have to run hundreds of synthetic tests through it to see if it works. Hypothetical scenarios, probe tasks, and possible edge cases. How does the system differentiate between a developer testing her limits and an actual real-world task failure?
This is a critical point of failure in a lot of AI development. If you mix the results of those synthetic test probes with her actual performance data, you completely skew her performance parity.
Right. If I give her 100 impossible calculus problems just to test how her error handling routes a failure, and she fails all of them because they are genuinely impossible, her overall success metrics plummet.
Exactly.
To the decision engine, it looks like her reliability has dropped to zero. She looks incompetent, but really, she was just taking a stress test.
Which is why the engineers implemented strict cohort separation. The system now requires metadata tags that separate real execution cohorts from synthetic or probe runs.
How does that work practically? Does the developer have to manually flag every prompt they send her?
Yes, or the environment itself dictates the cohort. The key is that her active learning, her maturity gating, and her self-confidence metrics are now based entirely on the unpolluted, real execution cohort.
So the test data is walled off?
The synthetic runs are tracked to ensure the plumbing works, yes, but they are walled off from her cognitive development loop. It is a level of rigorous data hygiene that you rarely see discussed in mainstream commercial AI applications. But it is absolutely foundational if your goal is actual reliable autonomy.
Okay, so the foundation is laid. We have the telemetry infrastructure acting as a highly sensitive nervous system. We have a pristine, unpolluted database thanks to the hard reset. But all of that data is useless if there isn't a brain to process the signals.
Right.
And that brings us to the core of the V2 update, the decision engine and the autonomous operator.
If the telemetry is the nervous system, the decision engine is the prefrontal cortex. It is the new cognitive center for autonomy. It is the component that ingests all of those rigid JSON payloads, analyzes the reason codes, and determines the next sequential action without human prompting.
This represents the fundamental shift from a reactive tool to a proactive agent. I really want to walk through a highly specific real-world scenario to illustrate this for the listener. Let's look at how this decision engine actually manifests in a complex 3D studio environment like Blender, because the document outlines an entire autonomous asset pipeline. Let's say the overarching goal set by the user is relatively simple. Create a new character asset.
In a traditional AI setup, even a highly advanced one, that goal requires constant micromanagement. You would have to prompt the AI for every single step.
Like holding its hand.
Literally. First, you tell it, find reference images. And once it does that, you have to prompt it again. Write a Python script to open Blender. Then, generate a base mesh using these parameters. The human is the decision engine, bridging the gap between isolated tasks.
But with the V2 closed-loop telemetry, Alita is supposed to chain these tasks autonomously based on the empirical outcomes of her previous runs. Let's walk through this hypothetical pipeline step by step. The user issues the macro goal.
The decision engine translates that macro goal into a sequence of runs. Run N1 is finding reference material. She executes a search protocol.
And crucially, because of the contract, our run 1 must return a JSON payload. Let's say she finds the images. The outcome status is success. The decision engine ingests that. It knows the prerequisite for the next step is met.
Exactly. So without human intervention, it initiates RUN2, starting the Blender application via API or CLI. The telemetry confirms the application process is running. Outcome status, success. It immediately moves to run in 3, executing the internal scripts to create the base model. Let's assume the mesh generates correctly. RUN 4 is a test render to evaluate the lighting and materials.
And this is where we need to dive into the error handling, because this is where the system actually proves its worth. Let's say the test render fails. Not a hard crash of the software, but a visual failure. The lighting is...
Right. The module itself cannot fix it, but it formats a strict run-end payload. The outcome status is failure. But more importantly, the reason code is flagged as validation failure, and the reason subtype might be exposure clipped.
So a normal automation script hits that error and just halts. It prints an error code to the console and waits for the 3D artist to come fix the lighting rig.
Right. But Alita's decision engine intercepts that specific validation failure payload. It analyzes the error context. It recognizes that an exposure-clipped subtype requires a modification of the lighting parameters in the previous step. It autonomously initiates Run N5.
Run N5 being a fix.
The goal of Run 5 is not to generate a new model, but specifically to analyze the lighting node values, apply a mathematical reduction to the emission strength, and push the update to Blender.
It effectively writes a patch for its own mistake in real time.
Yes. It pushes the fix, initiates another test render, validates the luminance values are now within acceptable ranges, returns a success payload, and finally moves to execute the export of the finalized asset.
That is just wild. She manages the entire messy, stateful reality of an active software environment. She is reacting to failures, adjusting parameters, and validating her own work without needing a human to hold her hand through the troubleshooting process. That is a massive leap forward.
Really is.
But I want to clarify something here because it's important context. She doesn't do all of this in total isolation. She doesn't have the entirety of human coding knowledge baked into her local parameters. And that brings us to the integration of external AI.
This is a crucial nuance in the V2 architecture. Alita is not a completely closed-off island. To solve complex problems, she is allowed to consult external massive language models. The document specifically mentions she can query the Codex command line interface or the Gemini CLI, among other local models.
For those who might not be deep into the engineering side, explain the difference between querying a CLI versus just opening a web browser and asking ChatGPT a question.
When a human uses a web UI, like ChatGPT, the interaction is heavily filtered. The web interface renders Markdown, it formats code blocks nicely, it adds conversational filler like, sure, I can help you with that.
Right, it's friendly.
A command line interface, or CLI, strips all that away. It is a direct programmatic pipeline to the model's API. When Alita queries Gemini CLI, she is sending raw data structures and receiving raw data streams back. It is machine-to-machine communication designed for speed and structural integration, completely bypassing the human-readable interface.
So she has direct access to the most powerful coding models on the planet. But the document uses a very specific, almost antagonistic phrase to describe her relationship with these external models. It calls them untrusted collaborators. Why the hostility? Why build a system that fundamentally distrusts state-of-the-art models?
Because treating LLMs as authorities is the fastest way to break an autonomous system. If you look at standard development practices right now, many human coders treat an output from Gemini or Codex as gospel. You ask it to write a Python script, it gives you the script, you paste it into your project, and you run it. You assume it is mostly right.
And when it's wrong, it breaks your entire build.
Exactly. Alita's V2 framework strictly prohibits that kind of blind faith. External models are never treated as authorities. They are categorized strictly as generators of hypotheses.
I love the analogy of a senior developer and an intern here. It's like Alita is the senior lead on a project. She hits a wall with that Blender lighting issue. So she turns to Gemini, the intern who has read every textbook in the world but has zero practical experience in this specific code base, and asks for a solution. Gemini hands her a script.
And as the senior developer, Alita does not just push the intern's code live to the production server. She takes that script and treats it as an entirely untested, highly suspicious hypothesis. Before that code is allowed anywhere near her active task, she must run it through her own rigorous local validation loop.
She puts it in a sandbox.
She sandboxes it. She executes the external code, and she measures the outcome utilizing her own telemetry contracts. If the intern's code throws an error, or if it fails to return the correct JSON payload, Alita discards it or attempts to debug it locally. She only integrates the external suggestion if it mathematically proves its viability within her own strict parameters.
She is effectively the quality assurance manager for the rest of the AI ecosystem,
That is exactly what she's doing.
which acts as a massive safeguard against hallucination cascades. If Gemini hallucinates a bad library call, Alita catches it in the validation phase before it corrupts her 3D studio project. This leads directly into the concept of capability gating, because even with all these safeguards, you don't just hand an AI the keys to your entire operating system on day one.
Autonomy must be earned. The V2 architecture employs strict capability gates. Fundamental high-risk actions like altering her own core files, performing deep system diagnostics, or modifying the root structure of a project are hard-blocked.
How does she unlock them? Is it a human developer deciding she's ready?
No, and that is the beauty of the closed loop. The gates unlock automatically, but only when her reliability is definitively proven by the cold, hard telemetry data.
By the numbers.
Yes. If her historical data shows a 99% success rate in sandbox file manipulation over 500 contracted runs, the system automatically removes the gate, granting her elevated privileges. Her freedom is directly tied to her mathematically proven competence.
Which is the perfect segue into the most grounded section of this update. We've talked a lot about theory and architecture. Let's look at the actual engineering reality. Section 6. The cold hard numbers. The developers published Alita's current report card. Where does the system actually stand today?
The document reveals that the overall project status for Autonomy V1 hardening is currently estimated at 68% progress.
68%. You know, I actually really appreciate that number. It isn't a marketing pitch claiming they've achieved artificial general intelligence and are ready to ship tomorrow. It is a very raw, transparent engineering reality check. Let's do a deep dive into the specific subsystems, because breaking down this 68% really grounds the reality of the work. Let's start with the highly functional components, the good.
The foundational layers are performing exceptionally well. The task execution core is sitting at 82%. The run artifacts writer, which is the system responsible for generating and formatting those strict JSON telemetry payloads, is at 78%. And the decision engine itself is at 76%.
So the fundamental logic loop is solid. Her ability to do a basic task, write the receipt, and decide what to do next based on that receipt is highly functional. But what about the layer above that?
That is where things start to drop off into what we can call the middle. The autonomous runner is at 70%. The reporting pipelines are at 72%. The learning execution pipeline is hovering at 69%. And the studio orchestration, which is the system responsible for chaining complex tasks together, like the Blender scenario we discussed, is lagging behind at 48%.
Why the massive drop-off for studio orchestration? I mean, if she can execute tasks at 82%, why can she only orchestrate them at 48%?
Because orchestration multiplies the complexity of the contracts. If you execute a single Python script, you manage one execution contract. If you orchestrate a 15-step 3D asset pipeline, you have to successfully manage 15 sequential contracts, where the input of step 4 relies entirely on the perfect structural output of step 3.
Right, it's a chain reaction.
Exactly. The compounding probability of a contract failure increases exponentially. The core works, but stabilizing a long chain of tasks without a single broken payload is incredibly difficult.
And then we have the genuinely lagging systems. The vision system is sitting at a dismal 42%, and the audio-voice pipeline is even lower at 38%. You briefly mentioned OCR earlier, but let's go deeper here. Why are the sensory inputs struggling so profoundly compared to the code execution?
It comes down to the friction between messy reality and strict mathematical contracts. When Alita executes a Python script in a terminal, the terminal provides a very clean, structured text output. If there is a syntax error, the terminal explicitly states the line number and the error type. It is relatively easy for the artifact writer to map that clean text string into a structured JSON reason code.
Because it's a structured environment feeding into a structured contract.
Exactly. But vision and audio are inherently unstructured analog-style inputs. If Alita is using OCR to look at a highly complex, customized user interface in Blender, and she misclicks a button by 3 pixels because the UI scaling changed on the monitor, the system doesn't generate a clean error log. Nothing happens. Or the wrong menu opens.
There's no stack trace for missing a button.
None. Mapping a visual anomaly like the screen doesn't look like I expected into a strict, standardized telemetry payload is a nightmare.
Because how do you mathematically define weird shadows or garbled audio in a JSON schema?
You can't, easily. The sensory inputs generate massive amounts of ambiguous data, and the strict telemetry contract fundamentally rejects ambiguity. That is why those systems are struggling to pass the validation layer.
But incredibly, the document states that the lagging sensory inputs aren't even the biggest problem facing the engineering team right now. The primary blocker holding the entire project back is a statistical dilemma they call the n less than 10 problem.
This is the direct, painful consequence of the hard reset we discussed in Section 3. By wiping away all the legacy pollution to create the clean learning window, they destroyed their sample size. Currently, they have fewer than 10 fully compliant real-world run-end events in the new database.
Wait, fewer than 10. They built this massive, complex infrastructure, and they only have single-digit successful data points. Why is it taking so long to generate compliant runs?
Because of the computational and structural friction we've been outlining. To generate one valid run, the system has to successfully observe, execute, measure, format a perfect JSON payload, correctly categorize the reason codes, pass the capability gates, and avoid the terminal guard states. The filter is so incredibly fine that almost everything is currently being caught and rejected as non-compliant.
And from a statistical standpoint, having an n of less than 10 is useless.
It is worse than useless. It is actively misleading. You cannot build reliable key performance indicators, or KPIs, on a sample size that small. If you flip a coin 3 times and it lands on heads all 3 times, a naive AI might conclude that coins always land on heads 100% of the time. The margin of error is massive.
Because the sample size is tiny?
Yes. If Alita succeeds 8 out of 10 times, the math might suggest she has an 80% success rate. But with such a tiny cohort, you have zero statistical confidence in that metric.
They need volume. The document explicitly states they desperately need a cohort of at least 50 pristine, contractually compliant runs just to prove the autonomy works mathematically. Until they cross that threshold, they can't trust the decision engine's long-term learning patterns. The system is essentially idling, waiting for enough perfect data to unlock its own potential.
And this brings us to the most practical question for the user. Based on all of these constraints, the strict telemetry, the missing data, how ready is she to actually take over your work?
Right. The developers provide a framework for this in Section 7, the 4 pillars of autonomy and the maturity model. They estimate the current autonomy readiness score is approximately 61%. To understand what that actually means, we need to critically analyze the 4 pillars holding up that score.
Pillar number 1 is execution reliability, currently estimated at 72%. As we noted, she can run tasks consistently. The reason this number isn't in the high 90s is due to edge case failures. If a third-party application crashes suddenly or the host machine runs out of memory, the exit path is completely unhandled. The system dies before it can format and send the required run-end payload. The execution contract breaks down during catastrophic interruptions.
Pillar 2 is measurement integrity, sitting at 58%, and based on our discussion, this low score is directly tied to the n less than 10 problem.
Correct. The infrastructure to measure is built and functional, but the statistical weight of the measurements is fundamentally untrustworthy until the sample size increases.
Pillar 3 is learning signal quality, currently at 52%. This is the lowest of the 4 pillars. Why is the learning signal so degraded?
This is the risk of synthetic data pollution creeping back in. We talked about cohort separation tagging test data versus real data. If that filtering mechanism isn't completely perfect, if even a few synthetic test probes bleed into her real-world telemetry, the learning signal degrades rapidly. The system is currently struggling to guarantee that 100% of the training signal is derived from pristine, real-world execution.
And finally, Pillar 4, self-direction at 60%. The decision engine works, as we detailed in the Blender pipeline scenario, but the document notes that there is still deep legacy fallback code in the system. When she gets confused, old heuristic scripts occasionally trigger, causing data mix-ups and preventing fluid, fully autonomous operation.
To contextualize this 61% readiness score, the engineering team mapped Alita against a 5-level maturity model for autonomous systems. And I think it is highly illustrative to compare these levels to where most standard software companies operate today.
Let's walk through them. Level 0 is defined as non-deterministic experimentation.
This is where almost every commercial chatbot and LLM wrapper exists right now. Every session is a roll of the dice. You prompt the AI, you hope for a good result, but you cannot guarantee consistency, and the system learns nothing structural from the interaction.
Level 1 is an instrumented system.
This is where advanced enterprise tools sit. The system logs what it does. It generates massive text files detailing its actions, but it still requires a team of human data scientists to read those logs, find the errors, and manually push updates to the model. The telemetry exists, but the autonomous loop does not.
Level 2 is a contracted system. This is the big leap.
Level 2 is where the execution contracts are strictly enforced. Every single action requires a structured, mathematically valid receipt. The system is designed to reject unstructured data entirely.
And according to the document, Level 2 is exactly where Alita is currently positioned. She has the contracts in place, but she is aggressively trying to cross the threshold into Level 3. Level 3 is defined as cohorted autonomy.
At Level 3, the system has solved the n less than 10 problem. It has enough pristine, cohorted data to statistically prove its own reliability. It can separate real-world data from test data flawlessly and use the clean data to drive the decision engine without human oversight. She needs those 50 perfect runs to secure Level 3.
Moving beyond that, Level 4 is a self-correcting system. The AI actively detects its own degradation, identifies its knowledge gaps, and autonomously initiates repairs or learning courses.
And finally, Level 5 is workhorse autonomy, a fully reliable, highly independent digital operator that can manage massive, multi-step projects across stateful environments with near-zero human intervention.
So looking to the horizon, where is all of this going? If they solve the data bottleneck and push her into Level 4 and Level 5, what does this look like for the user? The final section of the document paints a picture of the future. The proactive studio partner. We are moving far beyond the era of reactive prompts.
The transition from a Level 2 contracted system to a Level 5 workhorse represents a profound paradigm shift. It is the shift from a tool you use to a partner that possesses what the document calls autonomous project awareness.
Explain project awareness. Because right now, if I open an AI coding assistant, it only knows what I paste into the window. It has no idea what the overall architecture of my app is unless I spend an hour explaining it.
An AI with autonomous project awareness doesn't wait for you to type a command. It is persistently running in the background, utilizing that observe phase of its loop to monitor the entire pipeline. It will detect when a nightly code build fails on the server. You will notice when a 3D asset pipeline jams up due to a corrupted texture file. It will even flag when human developers commit code but forget to update the corresponding documentation.
That is incredible. But it goes beyond just flagging errors, right? Because an error reporting tool is just level 1. The document talks about autonomous task generation and skill expansion.
This is where the telemetry and the decision engine fully synergize. Because she is constantly measuring and analyzing her environment, Alita will soon be able to look at that failed server build and say autonomously, this build keeps failing due to a dependency error in a new library I do not recognize. I'm going to initiate a RUN sequence. I will find the documentation for this library. I will test a patch in a sandboxed environment. I will validate that the patch compiles, and then I will present the fully validated solution to the user.
It is the absolute pinnacle of the unfinished philosophy we discussed in the first episode. She doesn't pretend to know how to fix it magically. She recognizes her gap in knowledge, leverages her strict telemetry to guide her learning process, and executes a repair. But I think it is absolutely vital to emphasize something here. The ultimate goal of all of this massive engineering effort is not human replacement.
No, the stated goal is incremental autonomy. The vision the developers are pursuing is the creation of a digital studio operator that handles the repetitive, the analytical, and the diagnostic load. It is about building a system you can implicitly trust to manage the deep, complex plumbing of your project.
By taking over the tedious task of reading stack traces, fixing blown-out lighting renders, and managing JSON payloads, she frees the human user up to actually do the creative, high-level visionary work that machines still fundamentally cannot replicate.
To summarize this incredibly dense update, we've witnessed the leap from a philosophical concept, a fascinating unfinished AI, to a rigorous, mathematically enforced, telemetry-driven agent. She is still unfinished by design, but she is now actively building the hardened infrastructure required to measure her own growth accurately and safely.
It is a staggering evolution, from a loosely connected set of impressive party tricks to a system that literally refuses to function unless it can prove mathematically that it understands exactly what it's doing.
And as we wrap up this session, I want to leave you with a final, slightly provocative thought to consider regarding the long-term implications of this architecture. The entire Alita framework we've explored today is built on the absolute premise that an AI must be able to strictly measure its own errors to safely learn from them. The telemetry, the JSON payloads, the execution contracts, the decision engine, it is all constructed to enforce quantifiable self-measurement. But if the developers succeed, if they successfully build a Level 5 autonomous system that can proactively write its own tests, execute its own fixes, and validate its own learning entirely independently, Does it eventually reach an event horizon?
An event horizon.
Does it reach a point where its capacity to learn and adapt outpaces our human ability to measure and comprehend how it is learning? If the AI ultimately becomes the supreme, mathematically perfect arbiter of its own metrics, who is really holding the leash?
That is a brilliant and genuinely unsettling question to end on. If she builds the perfect flight recorder, eventually we might not be smart enough to read the data. Thank you so much for joining us on this deep dive update into the Alita V2 architecture. It is a complex, rapidly evolving story, and we will absolutely be here to cover the next chapter as she moves toward level 3. Until then, stay curious.